Again, in this video, we're going to go over section 2.6, part 3, which is on continuity. And so the first thing we're going to look at is theorem 211. And so this is what theorem 211 says. If G is continuous at A and F is continuous at G of A, then the composite function F composed with G is continuous at A also. Okay, so I'm going to look at a diagram to try to explain this theorem. Okay, so in this theorem we have two functions that we need to look at, right? We have F and G. Okay, so let's say this is the domain of G and A is some element in that domain of G. Okay, well G is going to send A over here to this point G of A, which of course is in the range of G. Okay, and let's assume the range of G is the same as the domain of F. Then F could take this element, G of A, and it would send it over to this element over here, F evaluated at G of A, which would be in the range of F. Okay, and so what this theorem says is if G happens to be continuous at A, and F happens to be continuous at G of A, then the composite function F composed with G is continuous at A also. And F composed with G is this function, this composite function that would take this element A directly to this element over here, F evaluated at G of A. Okay, so as long as G is continuous at A and F is continuous at G of A, then this composite function F composed with G would also be continuous at A. That's what this theorem says. Now there's a really nice result that we can pull out of this theorem that's kind of useful. Suppose you wanted to find the limit of this composition, F composed with G, as x approaches A. And we know that let's suppose we know that G is continuous at A and F is continuous at G of A. Okay, as long as I know those two conditions are true, then I know F composed with G is continuous at A. And if I know F composed with G is continuous at A, then by the definition of continuity at a point, I know what this limit's equal to. It's simply F of G evaluated at A. That's the definition of continuity, right? I mean, if F composed with G of X is continuous at A, which would be true as long as you satisfy both of these conditions, right? Then, by the definition of continuity, this limit as x approaches A is the same as F evaluated at G of A. That's the very definition of continuity. And so kind of the nice result of this is I can actually use direct substitution to evaluate the limit of a composition of two functions, as long as I satisfy these two conditions, right? G needs to be continuous at A, and F needs to be continuous at G of A. Okay, so that's a very useful result from this theorem that we can use to evaluate the limit of the composition of functions as x approaches A, right? We can simply substitute A into the function, into the composition. Okay? In other words, you can use direct substitution to evaluate the composition of F and G. Again, under these conditions, that make sure these conditions are satisfied. But if those conditions are satisfied, then yes, you can use direct substitution to evaluate the composition of F and G. Okay, so let's go back and look at example 4. So let's find the limit of this composition. So we want the limit of this composition of functions as x is heading towards 0. Now this really is a composition of two functions, so let's talk about that. Okay, so first of all, yeah, this is a composition of two functions because you can write this inner function as g of x. And then you can write this outer function as x to the 10th. All right, we're going to call that one f of x. Now we're going to show that the composition f composed with g is actually continuous at 0. If we can show that it's continuous at 0, then we can evaluate this limit using direct substitution. Okay, so how are we going to show this is continuous at 0? We're going to appeal to the previous theorem that we just mentioned. So in the previous theorem that we mentioned, we need to show that g is continuous at 0, and then we need to show that f is continuous at g of 0. And if you plug a 0 into g, notice that you get 2. So as long as we can show both of these conditions are true, then by that previous theorem, we know that the composition f composed with g is continuous at 0. Okay, so let's see if we can't justify these two conditions. All right, is g continuous at 0? Well, this is a rational function, right? And we have a theorem from the last video that said rational functions are continuous at every x value so long as the denominator is not 0. Okay, but if you look at this denominator here, this is never equal to 0. This is always positive for any x value that you plug in. And you know that because these are even powers. So any number you plug into here, into here, will generate a positive number, and then you're going to add 1 to it. Okay, so you'll never get 0 here on the bottom. Okay, no matter what x value you pick, you'll never get a 0 here on the bottom. So this function is continuous everywhere. In particular, it's continuous at x equals 0, which is the point we need it to be continuous at to satisfy the theorem. Okay, now f of x, which is x to the 10th, that's simply a polynomial, and we know polynomials are continuous at every x value. And so in particular, this is certainly continuous at 2, which is g of 0. So we've satisfied both conditions of that theorem, and so f composed with g must be continuous at x equals 0. Okay, all right, well, if we know this composition is continuous at 0, then by definition, the limit of, so let me write this out, the limit of f composed with g, right, if it's really continuous at 0, is the same as f evaluated at g of 0. Okay, that's the very definition of continuity. Okay, so if I know f composed with g is continuous at 0, then this must be true. Okay, and this limit right here is the same as this, right? That is f composed with g. Okay, and so let's see what f evaluated at g of 0 is, and then we'll know what this limit is. Okay, well, we know g of 0, you plug a 0 in for g, you get 2, right? So this is f evaluated at 2. And then when you plug a 2 into f, you get 2 to the 10th power, which is some big number. Okay, you can put that in your calculator to see what it is, but that's the limit. Okay, that's the limit of this composition. Okay, so that's how you would apply that previous theorem, right? This is a good case, a good example showing you how to apply that theorem that we talked about. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.